right, good morning, everyone. We continue with our MOOC course on distributed acoustic sensing using fiber optic cable. And today we have the pleasure of having Athena Chalari from Silixa, which is part of Luna Group company with us. And Athena would take us to the world of geothermal and dams, would tell us what's in one can get from DAS data on these environments. So Athena, floor is yours, or stage is yours. Yeah.
Thank you, Alireza, for inviting me, and thank you all for attending this course. I have been working with Silixa for the last 13 years now as a business development manager, looking after the natural environment sector. And today we will present how distributed fiber optic sensing systems can be applied for tailings dam monitoring and geothermal. So I know that you have already had a DAS session and a fiber optic session with our IP sensing colleagues. So we thought today to go more on the application side and focus on two applications, which is the monitoring solution on dams and geothermal system, and present to you the application and some case studies. If you don't mind, I will have a short introduction on Silixa and the company, and then refresh your memory on with a technology overview, and then we can start discussing the applications. So Silixa was established in 2007 to develop and commercialize distributed fiber sensing systems mainly for temperature and acoustic sensing. Now we can supply optical fiber-based distributed acoustic, temperature, and strain sensors. Our core offerings are highly innovative distributed fiber optic sensing solutions for oil and gas, environmental, industrial applications. And the company's markets and application include alternative energy, geothermal, CO2, CCUS, oil and gas, obviously, mining, defense, and academia. Our headquarters are in London, where we have also our production and technology labs. We have offices in Houston and Montana, a hub office in the Netherlands, and we're working with agents in the Middle East, in China, in Japan, Malaysia, with projects all around the globe. Silixa is an award-winning company. Our latest award is the Queen's Award of Innovation for our Carina sensing system, which is an enhanced resolution DAS system. And at the end of 2023, we have been acquired by Luna. And together with LEOS and OptaSense, we are a Luna sensing element. So very briefly, going on the technology, it comprises the distributed fiber optic sensing system comprised from an interrogator and the fiber optic cable. The fiber optic cable is the sensing element, and that is a very flexible sensing element that it can be deployed in many ways, which will enable gather information with a very dense spatial resolution along many kilometers, and at the end having a permanent monitoring solution that will not lose information compared to an array of point sensors, and will give the benefit of when the cable is into the ground, then we have a cost-effective system that we can do time-lapse surveys and with a very low environmental footprint. The principle is you have a laser into the box that emit laser pulses. The laser light generates these pulses that are coupled into the optical fiber. The optical fiber is like a glass tube. So the light is coupled in this glass tube. The backscatter light signal is sampled then in time, And the measured signal over time corresponds to a spatial sampling interval, which is equivalent to the two-way pulse width. The measured signal is spatially distributed from using an optical time domain reflectometry, and we have spatio-temporally continuous data over many tens of kilometers of optical fiber. So the optical cable is measured the whole length simultaneously. Within the same cable, we can have several fibers, and that way we can plug the fibers in interrogators with different lasers, and we can measure several parameters. One parameter is the static strain, and we are measuring static strain from the Brillouin backscatter. From the relay, we're measuring acoustics, practically measuring dynamic strain changings along the fiber optic cable. And from the Raman, we are measuring the temperature, distributed temperature sensors. You have probably seen this plot many times. The relay will be at the same frequency as the incident of light. The Brillouin, we have a small frequency shift that measures the static strain. And from the Raman blue shifted stocks to the red shifted, blue shifted understocks to the red shifted stocks ratio, their intensities, we can measure the temperature. Now we are offering interrogators with different characteristics based on the requirements of its application. For the DAS, in Silixa, we have the IDAS multi-gauge length, and we have the Carina sensing system, which is an interrogator with enhanced performance. The Carina, additional to the single mode and the multi-mode standard fibers that have, in a chaotic way, the scatters inside the fiber, it can operate with what we call engineered fiber. The engineered fiber has enhanced scatters along the fiber that we have, the commercial name is Constellation, but these enhanced scatters are in very specific location that match the gauge length of the unit and the application. And this all is giving more photons back, but in a very controlled way. So the Carina itself has a powerful laser that together with the engineered, when it operates on an engineered fiber, it can provide a 20 decibel improvement in the signal to noise ratio, which is 100 times more sensitive measurements at the end. Very briefly, the standard fibers. Multimode fibers are mainly used with the DTS systems, allowing many modes of light traveling inside the fiber core, which is a bit wider than the single mode fiber, where you have one single mode of light traveling in. This is mainly used by DSS system. For the DAS systems, we can use both. More common is the single mode, but multi-mode also can be used. On the cables itself, we have many cable designs, depending on the application requirements, from tactical cables, where it's mainly used on surface installation, trenched cables, to steel armor cables. These are thin cables. You will hear from cable manufacturers the term thin fiber into metal tube. So we have a metal tube with the fibers in and steel armor protecting it. This is mainly for mining application or into shallow boreholes in geothermal or environmental applications. And the double steel tube, this is typical cables for CCS or geothermal, but deeper application that can go to high temperatures. Now, going to tailing dams, what we ideally would like to have is the cable installed during the construction phase, that we can deploy the cables at the unsaturated area downstream. But if we have an existing dam, the system is also retrofitted. So we can deploy cables at the crest or the toe or even between depending what the operator allows, and some nice photos from during the construction phase of tailings and embankment dams. The main cables that we will be using for dam applications is tactical ones. This is tight buffered cables that are very easy to deploy. They don't have any memory and can be trends. So the very typical one will be this one with a double jacket to make it even more robust, and a rod deterrent to avoid any chewing from animals. And if there is an existing dam, for example, and we want to put it into sand pipes downstream, we can also use a steel armor cable. The main concern in dams is the internal erosion, and the internal erosion occurs when the water that seeps through the dam carries soil particles away from the embankment or the tailing, leaving voids in the structure. So without any intervention, this erosion may finally lead to failure of the dam. Consequently, early detection of any internal erosion effects is of key importance to reduce risk and ensure the safety of the dams. And we can measure the dam with many parameters. We can do a dam bridge detection through continuous monitoring of strain, of seismic activity, of any movement, of deformation or subsidence. And all this can be detected at the early stages. With the DTS, the distributed temperature sensor, we can detect seepage flow and calculate the seepage rates. With the IDSS, on measuring the static strain, we can detect the earth movements along the dam and identify the strain loads on the cable. With the DAS, the distributed acoustic sensor, and advanced imaging techniques, we can identify nonconformities and regions of concerns within the structure, saturated regions, identify voids and material changes. And by having an edge computing platform, we can integrate all these parameters and provide dense data sets that we can send to a cloud to the operator or process on site. And all this with a minimum environmental footprint, with large spatial coverage, more than tens of kilometers, a spatial resolution, a dense spatial resolution down to 25 centimeters for the temperature, and autonomous real-time visualization to the client system. And this is a low-maintenance system that does not require any calibration or have any moving parts or electronics. And we can measure multiple applications real time, basically. For the DAS in particular, we are using multi-channel surface wave analysis techniques by having active sources and be able to see the near surface characterization. We can create our S-wave velocity models, like the ones that you see here. Or we can go to ambient noise interferometry, so measuring passively, detecting structural saturation anomalies. And by using the same cable, we can measure not only where the cable is, but be able to image the near surface, image the whole structure of the dam, and measure multiple parameters by having multiple fibers within the same single cable line. Now, with the system architecture can be the interrogator on site, the fiber optic cable installed as I saw in the previous slide, the interrogator like a cabin or a control room on site where you have either only the interrogators and you are with a network switch, you are sending the data via a cloud to the operator control system, to their SCADA, to do the application at their premises. Or we can have on-site processing servers where we are doing the processing and the application is running on-site and we are simply sending the process data together with the raw data. So how the DTS will work, this is based on our exit temperature application. The system, we need a system calibration. So the system calibration will happen with a reference measurement of several months to monitor the environmental temperature. Then the modeling will be based on the material properties of the dam and the seasonal temperature variation to set different thresholds. And after setting the thresholds, we convert seepage into volumetric flow, liters to second, and identify how much fluid escape from the dam. So we see a significant increase in speed and increase in flow rates that potentially highlight issues. And this is how the exit looks like. You can see here an event of temperature, a temperature increase, that we have set a specific threshold of 2 degrees Celsius and set alarms above this threshold. And possible explanation is the increased seepage or rain or snow melt. But when we are monitoring the dam the whole year, and after modeling, we are able to distinguish the reason of the event. Obviously, it's not very easy to present a case study from tailings. These are in most of the times confidential information, but here we are presenting a case study on an embankment dam, which is a similar deployment. This is Moose Creek Dam in Alaska, where we have deployed 500 meters of optical cable at 2-meter depth into a trench at an area where in the past they had reported pinholes to large sand boils after some flood events. And the objective was using the distributed fiber optic sensors as an automated and early warning system to detect anomalies well before they're physically visible. We did trends. We used a plow to deploy the fiber optic cable and then covered back with sediments for good coupling. And we did some testing using relief wells. And you see here an increase in soil water temperature of up to 13 degrees Celsius, detecting during the testing, along with a section of known distress locations where that was not visible before with other instruments. And sorry, this was also in a study, and this is a published study that you can find online in collaboration with the US Army Corps of Engineers and Silixa. Now, going to geothermal monitoring, Silixa has been involved in different types of geothermal systems, from ground source heat pumps, which is shallow geothermal system, open loop or closed loop, to mine water energy, so how we can extract heat from abandoned coal mines that are filled with water and shallow aquifers, to deeper hydrothermal systems that have temperatures up to 260 degrees, and enhanced geothermal system like the forge, again at quite high temperatures and to granite. And the solution is based on not only providing the interrogator box, but designing the monitoring array, then deploying the fiber optic cable and the systems on site and set up the system, to functional specifications like Silixa's Edge platform, where we can have real-time fiber optic monitoring on an edge-based solution. And that will allow and cover many monitoring requirements like the reservoir characterization, seismicity, induced seismicity monitoring, flow allocation, the well integrity. And obviously the system benefit is that we have a permanent monitoring solution there with real-time and remote access and a low environmental impact with high sensitivity. We will ideally want for geothermal system a permanent installation. The permanent installation will allow time-lapse, but we will also allow microseismic event detection and localization, so to monitor the induced seismicity. We can deploy fibers in production or injection wells, and we can deploy also fibers in monitoring wells. And these wells can be daisy-chained. So when we have a permanent deployment, you see here the casing, the cable will clamp outside the casing, then we lower down the casing and we cement, and the cable will be well coupled with the formation, provide good quality of data. We can have on-demand seismic surveys, so vertical seismic profiles and imaging of the subsurface. We can measure with DAS and simultaneously with the DTS. So the DTS can also be used at early stages for monitor the cement curing process. We can see interconnectivity between the wells and measure flow allocation, temperature distribution monitoring to enable dynamic reservoir injectivity. And then we are bringing the signal from downhole with the surface cable to our control room. And inside the control room, we can have on-site the different interrogators to measure the 3 parameters, temperature, strain, and acoustic. We can have data storage on-site, but also enable remote access for quality control, or have data processing servers on site based on our rights platform to do all the applications there, and then send the data to the operators using a cloud system. The cables then can be deployed in many ways. Ideally, for a permanent installation, we would like behind the casing cemented, well coupled with the formation to enable also time-lapse surveys. But we can go on tubing, production or injection tubing. This is a semi-permanent installation for brownfield development, or wireline slickline installation like we do in oil and gas for an intervention where you will require surface service. Or if we have existing wells, and these are all typically observation wells, that it's the only way to monitor the geothermal plant, the geothermal field, is to have suspended system, and this is a semi-permanent installation. For the downhole, typically behind the casing, on geothermal, on deep geothermal that reach high temperatures, we can use its double steel tube cables up to 260 degrees Celsius. This cable has an internal tube, the fibers are in a loose tube, then you have a belt to avoid any slip between the outer tube and the inner tube. You can go to 300 degrees with polyamide coated optical fibers, or you can go to cable designs where you will have the DAS and DTS measurements in a loose tube and a tight buffer fiber for the static strain outside. The architecture of the system is having one line of cable going down into the well, and inside the cable you will have 4 to 6 fibers. The multi-mode fiber will loop together, the single mode will be looped together, and create loops inside the same cable. These splices at the bottom of the cable will be protected with a downhole assembly. So the optical signal will go down and up, and then in a junction box, it will be spliced with a surface cable, trench, and meet the next well. So that way we can have clusters of wells connected together and measure simultaneously with a single optical path, and we can bring with a surface cable the optical signal back to the control room where we have all the interrogators and the servers, and we can do our data storage, processing, and acquisition. If we have the edge platform system, we can have an edge scheduler that will tell to the systems for how much time they will interrogate each cluster of wells or each well, and with what configuration parameters, and then jump to the next cluster and repeat the cycle. We can have single distributed plots or multi-pot plots, and integrate that with point sensors into the wells. So the system is completely scalable architecture. It's a modular system that can be quite simple or have all the applications there. And the main applications are these. You can have vertical seismic profiles, so you can have your frequency spectrum, see the raw data, see the stack data, see how the signal to noise ratio improves with the stack data, and make any corrections and do the quality control, convert to SegWi files, have thermal profiling plots with the DTS, temperature to distance, temperature to time, and multi-mode plots with the DAS together, DAS and DTS together, continuous acoustic data, and casing integrity by combining also data from data loggers. Another module is the module for induced seismicity, microseismic event detection. And if we have cables installed in more than one wells, we can also be able to localize the event based on event location catalog, magnitude calculation, SegWi output, and a 3D visualization of the microseismic event cloud. From the apex of the event, PNS waves, you can see how far is the event from the fiber optic cable. As I said, during the cementation process, we can, with the DTS, we can monitor the cement curing. The cementation is an exothermal reaction, so you see here how the temperature jumps when the cement starts curing, and the thermal plots. And we can combine if we have a well that is stimulated in different zones. So what we are doing now, we are combining information from pressure. We see in the deeper zone how the fractures are opening during stimulation. And when we jump to the zone above, we'll see that this is not active anymore, and fractures above start activating. And that way we can also see fractures, we can do fracture rock characterization and see if any fractures are connected, go to zone 3, and so on. Going in some geothermal case studies. I don't know how good I am with time. This is the Utah Forge site. Forge is Frontier Observatory for Research in Geothermal Energy. So practically we are testing different technologies to find the optimum cost-effective technique for geothermal monitoring on an enhanced geothermal system. This is sponsored by the US Department of Energy. and comprises of 3 wells. This is a seismic monitoring well that was the first one that was drilled, and then the production well and the injection well. So we have fibers into the observation well and into the production well. In the observation well, we have single mode fibers. In the production well, I think there was an issue with the single mode fiber, so we are operating the DAS system on a multi-mode fiber. And you see here also the injection well parallel to the production. And in the control room, we have an Ultima DTS unit. We have our IDSS system to measure any deformations. We have our IDAS system for the acoustics, our edge control. The IDAS is sitting on an anti-vibration table to absorb any vibrations and provide better results. And we have also a data storage RAID. Here for these downhole techniques, we will be mainly using 10-meter gauge length. That is also comparable to a geophone array. They started with a circulation test. They drilled the production test in April 2023, and then they did the first circulation test. Here you see the casing, the cross-coupling clamp, and the cable clamped here onto the casing. This is a cable, and a centralizer to protect the cable as the casing is going downhole. Then we have the second circulation test and some results. We were able to identify 257 microseismic events. And the 3D modeling that was generated from the DAS data was in good agreement with surface station location that you see here in blue. The DAS is in red from Nims et al. In 2024. Another installation is shallower geothermal. This is at the UK Geoenergy Observatory in Glasgow, in Scotland. BGS, the British Geological Survey, is the operator of this site and the owner. And there are abandoned coal mines that are filled with water. And the aim is to have geothermal energy for mine workings at scale and provide to academia and industry a living lab, a research facility that they can go and do testing of different technologies. Silixa was responsible for providing the interrogators and cable deployments. So what we have here is a bit different cables. Because we had ERT at the well, everything was plastic. The casing was plastic, the centralizer is plastic, and you see here plastic cable ties to secure the cable outside the casing and then grout. The cable was a hybrid cable that includes two copper components that can be connect together and create a closed circuit. Then we are using a heat pulse system together with the DTS, induce power into the cable. We are heating the cable and we're measuring the heating and the cooling phase of the cable. That way we can measure the apparent thermal conductivity. We can see inflows into the well and help us better to measure the temperature, and it's called an active DTS technique. But we can also measure passively if we don't heat the cable, just with the DTS. So here on side, you see an abstraction and reinjection well and an environmental baseline borehole. At this enclosure here, we have our DTS system. This is an XT DTS with a reference bath. So we have a reference coil of fibers here to do our DTS calibration. And we can also bring a DAS and measure and do, I think University of Bristol has done some active seismic surveys with a small seismic source, and this work is published, plus some work on the DTS using the abstraction reinjection and the response. A similar field is the UK Geoenergy Observatory at Cheshire. The difference here is at the parking lot of the Chester University, we have 21 boreholes. Again, BGS is the operator of this site. Silixa was responsible for the setup of the system, the whole distributed fiber optic sensing solution, basically. We have, again, hybrid cables outside the casing grouted with the formation, and we have steel armor cables into the heat exchangers. Some of these boreholes have also heat exchangers. You can see here the fibers getting out of the wells into the junction box. Here at the junction box, they are spliced to the surface cable that it strands and go to the next well. And we bring the signal back to the control room where we have all the equipment. Here is the heat pulse unit and the relay system that can enable heating the wells, the 21 wells separately or in clusters of 5. The architecture of this site was that we are creating 4 clusters, and each cluster includes 5 wells, each well of a different type. These wells were connected with surface cable to form the cluster. The multimode fibers were connected with the DTS system that has multiple channels, that has 8 channels, that was controlled by the heat pulse unit and the relay, where we were connected the copper elements inside the cable, the hybrid cable. The single mode path were connected to the IDAS and have an optical box where we have again more channels. And the constellation fiber, because these cables also include engineered fibers, can be connected to our Carina sensing system. On site, we have the edge platform where we have a scheduler to tell the system what to interrogate and for how long, which clusters of wells, and to enable quality control remotely, data storage outside, but also send the data through a cloud to the servers at the BGS. And I will close this presentation with a case study from Succeed projects. Succeed is an ACT-funded, it has now finished, with 2 different sites, one in Kizildere and one in Iceland at Heliceidi. This is a CCUS project, so the aim is to reduce CO2 emission by storing CO2 while enhancing the geothermal performance. So maintain the reservoir pressure, increase the reservoir permeability, and understand what is happening when we re-inject the CO2 into a geothermal field. Now, the site of the Gizildere hydrothermal plant in Turkey, the reservoir is 2 to 3.5 kilometer depth, and the temperatures is approximately up to 245 degrees Celsius. The idea was from the produced raw gas piped from the geothermal plant, was injected directly into the wells with a compressor or a booster system in an injection of 700-meter depth at the supercritical state. So what we have here, we have 2 wells, observation existing wells, where what we did is use this suspended system. So this is a double steel tube fiber optic cable that we clamped together with a wire. See here the cable that is deployed simultaneously with this steel wire, and they were clamped together to hold the cable weight, and with this wellhead adapter remain into the well for several months. at these very high temperatures, at 260 degrees. Here is a junction box where we are connected the downhole cable with the surface that goes to the next well, and also have this T-shaped installation on the surface for being able to do also some surface seismic. We use the helically wound cable connected with the tactical cable in the surface. What we managed to do is a VSP baseline server, and in the future, when the CO2 would be injected for plumb migration, seismicity, and production optimization. And this is some preliminary results from the baseline survey to enable also time-lapse monitoring of the injection process. And the final site is at Helliseiði geothermal field in Iceland, where here the installation is different. We have only surface installation. We use this caterpillar, which at the same time is used as a plow. You see here the fiber optic cable. This is a huge reel of cable because what we are using is a helically wound cable, and I will explain what is that. We deploy the cable in the ground, and then we cover with sediments for better coupling. So this is an installation. We stop every few meters. We check with an OTDR system the cable integrity, and we continue the installation. The helically wound cable, as you know, the DAS is a one-component system. So in direct P arrivals, it won't be that sensitive. And how we improve that when we have a surface installation, we improve it by having helical wrap the fibers helically inside this cable that you have seen. We have taken the jacket out, and you see how the fibers are helically wound around an element, a central element, and we improve our detectability, our sensitivity in direct P wave arrivals. Using an E-wide seismic source, we were able to do the P velocity modeling and detect more than 108 events. Some of them were local events on induced seismicity close to 0 magnitude, and some of them were events of 4.3 magnitude around there. So, thank you so much.
Thank you very much, Athena, for this instructive and very clear lecture.